Alright, so we're continuing on with the previous video. So one thing I want to note with example 3 and example 4 is that these are focused on things that are different. So in other words, this is swimmer A, swimmer B, swimmer C, swimmer D, so on and so forth. And then over here with example 3, we had letter A, letter B, letter C, and letter D. And we were figuring out, different ways to put them in order using permutations. And again, permutations are when the order matters. In other words, this is different from this, is different from that, is different from that. Later, we're going to see combinations has a different rule. Now, the tricky thing with permutations is that sometimes we're talking about words or just situations where things aren't so different. So we're going to look at the word banana. So here, B-A-N-A-N-A. And we're going to be looking at the different ways that we can have a permutation of the word banana. Now, if I was looking for a combination of the word banana using all the letters, it's going to basically tell me, hey, you already put all the letters together. It doesn't matter. A permutation, on the other hand, actually considers each one of these letters to be different from one another, even if they look the same. Okay? So in this case, we're talking about a distinguishable permutation. So before we do that example, I want you guys to go ahead and write down this. So distinguishable permutations. Suppose a set of n objects has n1 of one kind of object, n2 of a second kind, n3, so on and so on. The number of distinguishable permutations of the objects is given by that formula. Okay? So, in other words, first we need to look at all the different types of the objects that we have. In this case, our objects are letters. So, we're going to call B n1, A n2, and then N n3. Here I have to count how many of each there are. For B, I only have one. For A, I have 1, 2, 3. And then for N, I have 2 of them. And here's what I'm talking about in terms of them being different. You can almost think of it in a way as the permutation looking at it this way. At B1, I have A1, N1, and then I'm back at A, so now this is like A2. Then I have N2, and then I have a third A. Okay? So in a way, you can think of it this way to make it a little less confusing. But what we're saying is that A2 and A1 and A3 are kind of different from each other, so putting them in a different order makes up a new combination. In other words, if I were to write banana again, but I switched the order of my A's, so let's say A3 is here now, A1 is over here, and A2 is over here. And let's go ahead and keep these two the same. This is actually a different permutation than this one. So even though it's still banana, it's a different banana, all right? So how do we calculate this? Now that we have all of these numbers, first off, to use this formula, n factorial, n1 factorial, n2 factorial, n3, ... n whatever number factorial, I need to know first what A is, or n is. N is made up of all of the different objects. In our case, letters. So it could be 100 different things. Thankfully, we only have 3 letters here, so n is going to be equal to that 1B, the 3 A's, and the 2 N's. So the n value for this problem is 6. And now we have all of the values we need in order to calculate how many permutations of the word banana there are for, well, banana. Okay? 6 factorial over n1. I have only one of those, so I'm going to put 1 factorial. n2, I have 3 of them, so 3 factorial. And then n3, I have 2 of them, so 2 factorial. Listing it all out, I have 6 times 4, 5 times 5, sorry, times 4 times 3 factorial over. I'm going to keep these the same way, so 3 factorial times 2 factorial times 1 factorial. 3 factorials cancel out, the 4 and the 2 will simplify, so I'm left with 6 times 5 times 2 over 1. That's going to give me 60 ways to write the word, to use the letters of banana to make up different orderings of the letter, all these letters. So instead of writing it all out, I'm going to show you that here are all of the 60 ways that are possible with banana. Okay? So you can see that. It's going to be fun listing that. All right? So that's going to wrap up for permutations. The last one I want to go over are combinations. So first things first, go ahead and copy down combinations of n elements taken r at a time. So the number of combinations of n elements taken r at a time is given by NCR equals n factorial over n minus r factorial times r factorial. Right? And I did state a little bit earlier that combinations are different from permutations in the sense that combinations don't care about the order. So before I go into that, I'm going to make a note that combinations order does not matter. And what do we mean by that? When we say that order does not matter, it means that A, B, C, let's say I put those 3 letters together, and then I have B, A, C. So this is a different order, and in terms of permutations, these would be 2 different permutations. For a combination, however, we're saying, well, it really doesn't matter. We're using the same 3 letters, so these 2 guys are the same. So in terms of counting this combination, combinations would ignore this difference because they're the same exact combination. So basically the number of outcomes with combinations is usually pretty much smaller. Right? Let's go ahead and look at an example, and this will be the last one. Example 6. Our question is, how many poker hands are possible? Now, for those of you guys who don't play with cards or don't play poker, the basic idea is that you have to have 5 cards, and you want a certain order, you want a certain number matching in order to beat another player's hands. In a deck of cards, we have to know that a deck of cards has 52 cards. That's actually very important for probability. And a hand in poker is 5 cards. Okay. So here we have to consider, okay, am I doing a permutation or a combination? If I have, let's say, an ace of spades, I'm not going to get too specific, and then a king, a queen, a jack, and a 10, and let's say they're all spades, just out of some random miracle. This is the same exact thing as if I put in my hand in this order: the queen of spades, the jack of spades, king of spades, ace of spades, and 10 of spades. These 2 hands are exactly the same, and again, they're both spades. So it doesn't matter in my hand what order I put it in. Like if I lay it all out, it's still going to be the same exact hand as this one. Okay? And that's the difference between a combination and a permutation. A permutation would say, yeah, these 2 are totally different outcomes. A combination says, no, these 2 are exactly the same, so we don't want to double count it. So knowing that, I need to first identify how many total objects I have, which is 52 cards. And then the outcomes I only want the outcome to consist of 5. So using my formula, NCR, I'm going to have 52 factorial over n minus r, so 52 minus 5 factorial times 5 factorial. Now this will be pretty big. We have 52 factorial over 47 factorial, 5 factorial. I'm going to go ahead and list it out very briefly. 52, 51, 50, 49, 48, 47, and we'll stop there. And we have 47 factorial and 5 factorial. 47 are gone. I'm left with 52 times 51 times 50 times 49 times 48. Let's see if we can simplify any further. 5 times 4 times 3 times 2 times 1. That's going to give me 20. 20 times 3 is 60. 60 times 2 is 120. So I can simplify a little further, but really this is a problem for the calculator. And the total number of poker hands out of all those 52 cards is going to be 2,598,960. If we had considered permutations, that number would probably be a lot bigger. Okay, so this is the total combinations of poker hands you could have, considering that there are different faces and different suits. All right, so that's the only example for combinations that we're going to do. Make sure that you understand the primary difference, because in your problems you're going to have to be able to distinguish and know which formulas to use. All right, so if anything at all confused or created some difficulty for you, make sure to rewind, replay, or write down questions to ask tomorrow. I know it's a lot, so please come ready. All right, have a good day, you guys.